Welcome to the deep dive. Today we're diving into what you might call an invisible crisis. It's a crisis of speed that has quietly become maybe the single biggest threat to efficiency inside the world's largest computing centers, these warehouse-scale computers, or WSCs.
That's right.
You know, if you've ever been frustrated by a slow app, you might blame your internet or a slow disk drive. But we're going to talk about a bottleneck that's way more insidious, one that lives almost entirely in the operating system.
It does. And in the programming models we all rely on, we're zeroing in on a time scale
Yeah.
that for a long time system architects just sort of neglected the microsecond.
Right.
We've had these two historical playbooks for dealing with delay. We get nanoseconds, that's processor cache speed, where all this sophisticated hardware magic happens.
We get milliseconds. That's the slow mechanical stuff like a spinning disk where the OS, software takes control.
Exactly. But right there, squeezed in the middle, between 100 nanoseconds and 1 millisecond, you've got the microsecond. And now this new powerful breed of I/O devices is showing up.
Things like cutting-edge networking, new kinds of memory.
And they are forcing systems built on these decades-old assumptions to just completely break down.
So our mission today is to give you a full picture of why these existing computer systems are just failing to handle these microsecond scale events. We're going to analyze the core architectural choices that, were perfect for the past but are now creating these massive bottlenecks.
And they threaten both performance and, this is the crucial part, programmer productivity across these giant infrastructures.
And here is the single most important idea you should take away from this deep dive. The core problem, it isn't the raw speed of the new hardware.
Not at all.
The problem is the cumulative software overhead. It's the price we pay for abstraction, and it can take a device with a blazing fast 2-microsecond latency and just inflate it by 50 times.
Turning it into a nearly 100-microsecond nightmare, all in software.
Okay, so to really appreciate the severity of this microsecond crisis, we first have to go back and look at the two big latency problems that computer architects already solved. I mean, brilliantly solved.
Right. And these solutions are what created the synchronous programming models that basically every developer on the planet relies on today.
So let's start at the fast end, the nanosecond scale. This is where speed is measured in, single-digit CPU cycles?
Pretty much. Think about accessing the L1 cache. That's maybe 4 nanoseconds. Or going a bit further out to your main DRAM, which is around 100 nanoseconds. It's incredibly fast.
And thankfully, programmers don't really have to think about this stuff.
Exactly. And that's the point. Decades of processor design solved this almost entirely inside the hardware. The genius architectural choice was to maintain a simple, synchronous programming interface to the memory system.
So when my code says load this value, the thread just. It looks like it just waits for the data to show up.
Logically, it just blocks. Whether that data is in the fastest cache or all the way out in DRAM, the programming model looks the same.
But that simple appearance is a complete illusion, isn't it? If a program actually stalled for 100 nanoseconds every time it needed to access DRAM, our processors would be idle like 90% of the time. Performance would be a disaster.
That is the core insight. The illusion is maintained, but the performance is achieved through these incredibly complex microarchitectural techniques. And they're all handled by the hardware, completely hidden from the developer or even the OS.
We're talking about things like deep instruction pipelines, branch prediction.
And crucially, out-of-order execution, or OO.
Right, OO lets the CPU look ahead. If it sees the current instruction is stuck waiting for data from memory, it just skips past it and starts working on other independent instructions further down the line.
Precisely. By constantly looking for other work to do, that out-of-order engine uses the waiting time to keep the execution pipelines full. And since nanosecond scale delays, even 100 nanoseconds are pretty short in terms of CPU clock cycles, the hardware can usually find enough other work to hide the delay.
So the wait is short enough, and the hardware is clever enough that the developer gets the best of both worlds. High performance and simple, easy-to-read, synchronous code.
It was a perfect solution for the internal CPU architecture.
Okay, so now let's jump to the other extreme, where hardware fails and we have to turn to software. The millisecond scale. This is where we run into those legacy devices like slow networks or the classic example, a mechanical hard drive, and I/O there takes 10, maybe 20 milliseconds?
Right. And this is the historical domain of the operating system. If a processor core issues a classic synchronous disk read system call, that CPU would be sitting idle for millions of clock cycles.
Which is a catastrophic waste of processor time, just terrible for throughput.
So computer scientists solved this using sophisticated software-based techniques. The most famous one, of course, is operating system thread context switching.
So the OS sees that a thread is about to start a slow I/O.
And it immediately performs a software context switch. It parks the waiting thread and puts another ready-to-run thread onto that processor core, so that the core stays busy while the first thread waits for its I/O to complete.
The genius of this model is really the math, right? The amortization, because doing a context switch isn't free.
Not at all. It's quite expensive, actually. You have to save all the current thread's registers, update kernel tables, find a new thread, load its state. The overhead is significant.
It's measured in microseconds.
Exactly. Let's put some numbers on that. A single context switch might take 5 to 10 microseconds. But if your I/O operation takes 10 milliseconds, which is 10,000 microseconds,
then the cost is tiny in comparison.
the cost of the two context switches, one to suspend the thread, one to resume it, is easily amortized. You're paying, say, 20 microseconds of overhead to make sure your processor is busy for 10,000 microseconds. It's a fantastic deal.
So the key takeaway from this historical playbook is that we had these two very clear dividing lines. Nanoseconds were hidden by low overhead hardware tricks. Milliseconds were hidden by high overhead software, but the cost didn't matter because the wait was so long.
But the very moment a device falls right into that microsecond gap in the middle,
Both of those brilliant solutions become completely useless.
they become toxic even.
And here's where we get to the modern crisis. The whole structure of our system optimizations is just fundamentally not built for the microsecond range. It hits the failure point of both of those strategies at the exact same time.
We are seeing this rapid evolution of hardware components that are driving raw latency down into that microsecond regime. And this just makes both the hardware out-of-order execution and the software context switching obsolete.
Let's start with networking, because that feels like the biggest change in a modern warehouse scale computer.
It's huge.
Yeah.
Network speed has just soared. With fast data center networking, 40 or 100 gigabits per second, the time it takes just to get a packet onto the wire is tiny.
How tiny?
Often less than a single microsecond, maybe 300 nanoseconds. And even just the speed of light, traversing the physical distance of a large data center, say 200 or 300 meters, that's only about 1 microsecond of delay.
So the raw communication is now in the low single-digit microsecond range. The network itself is no longer the bottleneck.
Precisely. Networking used to be considered a slow millisecond scale thing. It was a perfect target for OS context switching. Now it's blazing fast, and our software hasn't caught up.
And storage is right behind it, isn't it?
Oh, absolutely. Traditional raw flash devices are already in the tens of microseconds range, but we're moving towards these revolutionary new non-volatile memory technologies, or NVM.
Like Intel's X-point memory.
Exactly. Things like that are expected to deliver raw latencies at the absolute low end of the microsecond regime. You could be looking at 1 microsecond for localized access.
That's a complete game changer. It means storage, memory, and networking are all competing in the same tiny time window.
And it goes beyond just standard components. You see specialized systems operating here too, like the Stanford RAM Cloud project, an in-memory storage system that targets microsecond order latencies.
Or offloading small tasks to accelerators like GPUs.
Right. If you offload a small, fast computation, the time it takes to coordinate that offload also falls squarely into the microsecond scale.
So if basically all the I/O in a modern WSC is now happening in this microsecond gap, the failure of our old strategies affects pretty much every single thing the system does.
To understand why exploiting this is so critical, you have to look at the bigger picture, the macro-level shift in computing architecture. And it's really linked to the end of Dennard scaling and the slowing of Moore's law, which started to bite around 2003.
In simple terms, single-core processors just stopped getting exponentially faster.
That's the essence of it. Today's processors are about 20 times slower than what the old doubling rate would have predicted. So since we can no longer rely on faster single cores to solve our problems, cloud companies had to find a different way to keep up.
And that response was to scale out, not scale up.
Exactly. The only way to deliver high-performance services, web search, social media feeds, you name it, is to increase the number of computers involved in a single customer query. This is the very definition of a warehouse-scale computer.
Let's quantify that. When I type a search query, what actually happens inside that WSC?
Well, that single request from you needs to come back in maybe 50 to 100 milliseconds to feel responsive. But to achieve that, it kicks off a massive fan-out process.
Okay.
The query hits a front-end server, which then initiates parallel requests, remote procedure calls, or RPCs, to dozens or hundreds of other services, index services, ad services, ranking algorithms, storage systems.
And so that one search query from me translates into how many RPCs?
Thousands. A single top-level query can easily result in thousands of individual RPCs flying across the data center.
Thousands of RPCs for one search result. That's a staggering amount of communication.
And that is exactly why microsecond latency is a killer. If you have 1,000 requests, and each one has even a small chance of stalling because of some software overhead, those small delays add up fast. The total query time is often dictated by the slowest link in that chain, the tail latency.
So if the software overhead for just one of those 1,000 RPCs turns a 2-microsecond transaction into a 100-microsecond stall, the whole thing slows down for me, the user.
And this reliance on frequent fast I/O just exponentially increases the system's exposure to this microsecond bottleneck.
Which brings us to the consequences. If our systems are built on these old assumptions and now everything is a microsecond, where does all that performance go? You said it's burned by overhead.
It is. And the first failure point is those nanosecond techniques we were praising earlier. The out-of-order execution, the instruction-level parallelism.
They just stop working.
They fail entirely in the microsecond regime because the delay is simply too long for them to hide.
I need to get a sense of scale here. How many CPU cycles is a microsecond?
Okay, so a modern CPU runs at, say, 3 gigahertz. That means one clock cycle is about a third of a nanosecond. So 1 microsecond is over 3,000 clock cycles.
And a 5-microsecond delay is 15,000 clock cycles.
15,000, that's an eternity in processor time.
It's a huge number.
Exactly. And the hardware mechanisms we use to hide latency, they're just not designed to look that far ahead. The out-of-order engine has finite resources like the reorder buffer, which tracks all the speculative instructions. A modern chip might have a buffer that holds, say, 256 or maybe 500 instructions.
So if one instruction stalls for 15,000 cycles, the processor can only hide that if it can find 15,000 cycles worth of independent work among those few hundred instructions in the buffer.
And it just can't. There isn't enough instruction-level parallelism in that small window. The buffer fills up, the whole pipeline stalls, and the core just sits there, idle, for thousands of cycles, waiting for a few microseconds of I/O to finish.
So the nanosecond tricks don't work. And conversely, the millisecond tricks, the software context switching, also collapses.
It does, for the opposite reason. Its overhead is now too high relative to the speed of the device.
This is the core tragedy of the microsecond gap, isn't it?
It really is. As we said, the overhead of a software context switch, the kernel call, saving state, all of it, is itself in the microsecond range. 5 to 10 microseconds.
So if my fancy new storage device can get me data in 5 microseconds, but the OS context switch to manage that wait costs another 5 microseconds, I've gained nothing.
You've traded a 5 microsecond hardware wait for a 5 microsecond software wait. It's actually worse than zero gain. You've introduced complexity, non-determinism, more resource contention. The whole amortization model just breaks down.
The device isn't slow enough to justify the expensive software mechanism we use to manage it.
We have taken revolutionary fast hardware and completely nullified its performance benefit with the price of our own software abstraction.
The system is essentially defeating itself. We spend billions on 2 microsecond components, and then our own OS design makes them 10 times slower just by trying to be efficient.
The best way to see this self-sabotage is to look at a real-world breakdown of network latency. It shows exactly how performance is burned, microsecond by microsecond, entirely in the software stack.
Okay, let's do that. So we start with the theoretical minimum. You said the raw hardware time on a fast network might be around 2 microseconds. That's our baseline, using something like remote direct memory access or RDMA.
Right, RDMA is the baseline because it bypasses the OS kernel almost entirely. It offloads all the work to specialized hardware on the network card.
2 microseconds, that's our perfect world. What happens when we add the first layer of software?
First, we make it two-sided. RDMA can be one-sided. One machine just shoves data into another's memory. But most application logic needs a two-sided operation, where the remote machine has to run some software to process the request.
Okay, so that involves signaling the remote CPU.
And that alone adds several more microseconds. Then, once that CPU is signaled, the local software has to dispatch the event.
Meaning it has to figure out which application thread needs to handle this new data.
Exactly. And that dispatching involves processor wake-up, kernel scheduler activity, and that adds several more microseconds of latency.
This is already a cascade of small delays, and each one is compounding.
It is the death by 1,000 cuts. Next, you have to consider how the CPU is notified. High-performance code might use spin polling, where the CPU just burns cycles checking a memory location over and over.
But that's inefficient.
It is. So often, systems use interrupt-based notification. But an interrupt is hugely expensive. The CPU has to stop what it's doing, save its state, jump into the kernel, handle the interrupt, restore the state. That adds many more microseconds.
So we've added multiple layers of just system-level interaction, and we haven't even gotten to the application logic yet.
Not even close. Now you add a standard feature-filled RPC stack on top of that. The layer that manages protocols, serializes and deserializes your data, handles errors.
That sounds expensive.
It adds tens of microseconds all by itself.
And what if we just give up on the specialized stuff like RDMA and use the standard protocol everyone knows like TCP/IP?
If you use a full, general-purpose TCP/IP stack instead of an optimized transport, the cumulative effect of all these software layers pushes the total round-trip latency to over 75 microseconds.
So we took a 2-microsecond hardware fabric and turned it into a nearly 100 microsecond effective fabric. That's a 50-fold degradation.
An architectural failure driven entirely by the cost of software abstraction.
And beyond that explicit stack, there are other hidden costs, right? This data center tax.
The data center tax is this cumulative cost of all the generalized software overheads that are just always running. There was a study done at a major cloud provider that found something staggering.
What's that?
20 to 25% of all their processor cycles, fleet-wide, are spent on these low-level overheads.
Wait, a quarter of all the CPU cycles they buy are not being used for customer computation, but just for system maintenance and abstraction costs?
That's the death by 1,000 cuts. It's things like serialization and deserialization, memory allocation, network stack processing, compression, encryption, all these little things that chew away at your microsecond budget.
And one of the most frustrating hidden costs has to be processor sleep states.
Oh, absolutely. For power efficiency, cores go into deep sleep. When an RPC arrives at a core that's sleeping, it has to be woken up. Its caches L1, L2 are cold and have to be repopulated.
And that takes time.
That wake-up and cache warm-up latency alone can add tens to hundreds of microseconds to the transaction time, completely wiping out the benefit of your fast device.
So you trade power for huge latency spikes.
Precisely. And this problem is everywhere. Another project, Moneta, looked at a new non-volatile memory device with a raw latency of just a few microseconds. By the time they measured it through the OS, the effective latency had increased by almost a factor of 5.
Just from kernel overhead interrupts data copying.
It makes it perfectly clear. The system architecture, built around that kernel boundary and memory management, is the new bottleneck, not the hardware speed.
Which brings this whole thing down to a fundamental trade-off. All this crippling overhead, this 75 microsecond tax. It's the price we pay for simplicity. Specifically, the simplicity of the synchronous programming model.
That is the core tension. In these huge WSC environments, programmer productivity is everything. The synchronous model is overwhelmingly preferred at places like Google because the code is simpler, easier to write, easier to tune, and most critically so much easier to debug.
But hold on, if you're sacrificing a 10x performance hit on every single I/O operation, isn't there a point where that productivity becomes just too expensive?
It's a fair question, but you have to consider the environment. You've got a single code base being worked on by thousands of developers. They're putting new releases multiple times a week.
The cost of a bug is enormous.
The cost of introducing subtle bugs, race conditions, or state management errors in complex asynchronous code is often far greater than the performance penalty of the synchronous abstraction. So you shift that burden of managing complex events away from the thousands of app developers and onto a few specialized OS or library engineers.
Let's break down the benefits of that synchronous model architecturally.
Okay, in a synchronous API, the control flow is simple, it's sequential. A function calls an I/O primitive, say, read document index, and the thread logically blocks right there until it returns.
And all the context for that operation is just managed automatically.
It's stored implicitly right on the thread stack, the current loop index, temporary variables, whatever you're working on. It's all handled for you. The developer doesn't have to think about it.
There's a great example in the source material, a simple count words function.
It's perfect. The function first calls index lookup, which returns synchronously. Then it calls retrieve document, which also returns synchronously. Finally, it counts the words. The flow is clean, intuitive, and the state is managed automatically by the call stack.
Okay, now let's look at the alternative, the asynchronous model, which is what you have to do if you want to get that raw 2 microsecond speed.
Right. In the asynchronous model, your program sends a request and then immediately continues doing other work. It has to rely on some notification, a poll, or an interrupt to know when the data is ready.
And this just completely changes the data structures and the control flow, right? It pushes all that state management work back onto the programmer.
The control flow has to be broken apart.
Yeah.
Your computation gets split into these separate functions, often called callbacks or continuations. The flow becomes obfuscated, jumping between these disconnected pieces of code.
And the data structures have to move from being on the stack to being explicitly managed on the heap.
That is the critical point for productivity. In the async world, you can't rely on the stack because the function returns immediately. So you, the programmer, have to explicitly allocate and track all the state on the heap.
So for that count words example, I'd have to create my own special struct, like async count words state.
Yes, and that struct has to contain every piece of state you need, what phase of the operation you're in, the intermediate results, and crucially, a pointer to the next function that needs to run when this I/O finishes.
So my two simple sequential steps now become two separate callback functions, like redocument index done and redocument done.
And each of those callbacks has to take that state object, check its status, do the next thing, update the object, and then you have to remember to free that object from the heap when you're done. You are manually doing the work the stack used to do for free.
The code becomes a mess. It's prone to memory leaks, and it's a nightmare to debug when state transitions go wrong.
And even with modern language features like async await that try to hide the callbacks, the underlying complexity of managing that explicit continuation state is still a huge drain on developers.
So the fundamental dilemma is this choice between these two opposing models. We have a fast device and a simple programming model.
To reconcile them, the simple synchronous function initiates the I/O and then has to execute a wait primitive right there, blocking the thread.
And that wait is the microsecond barrier. The only established way to implement that wait is to call the operating system for thread scheduling.
Which involves crossing into the kernel, saving the context.
And paying that huge microsecond penalty that completely nullifies the fast hardware.
So you have an impossible choice. Use the simple synchronous model and pay a massive latency tax, or switch to the asynchronous model and pay a massive productivity tax.
The current system architecture gives us no way to wait synchronously for a microsecond without paying the full price of a heavy software context switch.
We are hitting an architectural wall where the speed of the hardware is now faster than the speed of the software abstraction we use to manage it.
Okay, so if the problem is this fundamental, if the software stack and the kernel are the bottleneck, then small fixes aren't going to cut it. We need a complete redesign of the system from the silicon up.
That's right. And when people think about high performance, they often look to high-performance computing, or HPC. But the source material makes a really crucial distinction here. HPC solutions are just not suitable for WSCs.
Because the goals are completely different. What does HPC prioritize?
HPC workloads, like physics simulations, usually have static, well-defined data structures. The code changes slowly. And their main goal is just raw peak performance. Stranding resources, having processors sit idle, is often acceptable if it gets the final answer faster.
Whereas WSCs, like a public cloud, are commercial. They're data-driven.
Exactly. WSC workloads are online, data-intensive, and operate on complex, dynamic data structures. The code is constantly changing with thousands of developers, so productivity is critical. And most importantly, the focus is on performance per dollar.
Performance per dollar. That means utilization is everything.
You cannot afford to strand resources. So the old supercomputer tricks of using massive hardware multi-threading to hide latency don't work because they often lower single-thread performance. WSCs need the best of both worlds, low latency and high utilization while keeping developers productive. And that demands custom solutions.
So the first place to look is redesigning the software layers to be microsecond aware, systematically get rid of that overhead we talked about.
System designers have to be ruthless. We need to optimize every single layer. We need software solutions that let an application coordinate I/O without crossing that expensive kernel boundary every single time.
What are some specific software optimizations that we need?
First, dramatically reduce lock intention. Standard kernel mutexes are way too heavy. We need lighter weight synchronization that can be handled almost entirely in user space. Second, we need lower overhead interrupt handling and more efficient ways to do spin polling.
So if a thread is spinning, waiting for I/O, it's not just burning power senselessly.
Right. The OS needs to let that CPU enter a lower power state without going into a deep sleep that would cause a huge wake-up penalty. And of course, the scheduling algorithms themselves have to change.
How so?
Traditional schedulers often prioritize fairness. We need new schedulers tuned for the microsecond regime that can prioritize threads waiting on critical path I/O, making sure resources are ready the instant the data arrives. The goal is to treat a 5-microsecond overhead as a catastrophic failure, not just noise.
But ultimately, software optimization alone isn't enough, is it? Not if we want to keep that simple synchronous model.
It isn't. We need new hardware support that allows synchronous blocking to extend into the microsecond range without the software cost.
This sounds like asking the hardware to basically do the OS scheduler's job, but at nanosecond speed.
That is precisely what's required. We need hardware for extremely fast context switching. We're talking about taking that cost from 10 microseconds down to the tens of nanoseconds, an overhead that's comparable to an L3 cache hit.
How could the hardware possibly do that?
It's all about efficiently caching the thread's context. Instead of saving it to memory, you'd have dedicated architectural structures, maybe a special-purpose context cache, a bit of fast memory on the chip designed solely to store and retrieve this data-parked threads.
So if the context is in that fast cache, the hardware can swap threads in tens of nanoseconds.
And effectively hide the microsecond wait. We also need better I/O orchestration built right into the chip, hardware to manage queues, to dispatch tasks.
And you mentioned this idea of a low overhead wait primitive, something like the monotone wait instructions. Can you break down how that solves the problem?
So instructions like wait are designed to bridge this exact gap. They let a thread yield, but based on a change to a single memory address without ever calling the kernel. Okay. The thread executes wait on a specific memory address, telling the hardware, park me, but wake me up instantly if this value changes.
So the I/O device, when it's done, just writes to that one memory word.
And the CPU's monitoring logic, which is fast, nanosecond scale hardware, detects that write and instantly wakes the stalled thread. It completely avoids the kernel call, the context save, the scheduler, the cache pollution, all of it.
So you get the simple synchronous programming model we want?
But with the performance of raw hardware speed, it's the holy grail.
And finally, let's talk about utilization and power.
Critical for WSCs. If a core is blocked for a few microseconds, we shouldn't keep it burning power. The hardware should let that core stop consuming power and shift that power budget to other active cores. This way, we maintain high overall system utilization, even if individual threads are constantly yielding for tiny waits.
So we've established a pretty clear and present danger in modern computing. These architectural decisions, like OS-managed threading and interrupts that were just noise at the millisecond scale, are now crippling, performance-killing bottlenecks at the microsecond scale.
The layers of extraction we built into software for reliability and simplicity, what we call the data center tax, now consume most of the time budget for our fastest I/O devices. The hardware is ready for a 2-microsecond world. Our software stack is holding us back in a 100-microsecond world.
And the path forward seems to be creating a virtuous cycle. We need new microsecond-optimized system stacks that attack that overhead, combined with the continued use of synchronous programming models to keep developers productive.
That combination is what will dramatically increase the effective computing power of these WSCs without sacrificing the most valuable resource of all, developer time.
So here's the provocative thought for you to take away. We've detailed how, when you're dealing with events measured in microseconds, the simple act of reading data is no longer the bottleneck. The true bottleneck is the cost of the abstraction we use to manage that simple act.
So if we have to choose between two necessary evils, sacrificing productivity for performance, or performance of productivity, what specific architectural layer should system designers choose to simplify or offload next? Should we redesign our programming languages to make asynchronous state management trivial? Or should we keep pouring hardware resources into the CPU to make synchronous state management effectively free? Where do you draw the line between software-managed simplicity and raw hardware speed?